Today I'll explain how to detect collision between a pyramidal frustum and an axis-aligned bounding box, an oriented bounding box, and a sphere. A pyramid is a geometric shape with a flat base connected by 4 adjacent triangles that meet at the apex. A pyramidal frustum is the cross-section of a pyramid that lies between the base and a plane parallel to it just below the apex. Pyramidal frustums are used to determine which objects are within the player's view. A pyramidal frustum has 6 faces, which are represented with planes: left, right, top, bottom, near, and far. The shape of the frustum is defined with 4 values: the viewing angle, which affects how much the player can see vertically and horizontally; the aspect ratio, which makes the near and far planes width proportional to their respective heights; the near plane distance, which represents how close the starting boundary is to the player; and the far plane distance, which represents how far the player can see. The world transformation of the frustum is defined by a position, which is the location of the viewer, the view vector, which represents the direction the viewer is looking in, and the up vector, which represents the orientation of their view. The planes of the frustum are set up so the normals are pointing away from its center. This fact is pivotal in the collision detection code, which you will soon see. Any point within the frustum is within the negative half space of all the planes. Any point outside the frustum is in the positive half space of at least one plane. An axis-aligned bounding box is a rectangle that has its axes aligned to the axes of the world. It is useful for rectangular objects that are rotationally static, such as a crate. It is defined by a position, which indicates its location in the world and its length, height, and depth. The frustum and axis-aligned bounding box function returns 3 possible states: inside, outside, and intersecting. Inside means all the corners of the box are within the frustum. Outside means all corners are outside of it, and intersecting means some corners are inside and some are outside. This function doesn't handle the edge case of the frustum intersecting a face of the box. In this case, none of the corners of the box are within the frustum, and the function will return outside. This function assumes that most of the boxes are smaller than the frustum, so this edge case shouldn't be much of an issue. This function tests every frustum plane against each corner of the bounding box. It increments the vertex out count if a box corner is found to be in the positive half space of a plane, and increments vertex in count if it's in the negative half space. It determines if a box's corner is in the positive half space when the distance function returns a positive value. The distance function creates a vector from the point on the plane pointing in the direction of the corner. It then performs a dot product with this vector and the normal of the plane. If the result is negative, the point is behind the plane. If the result is positive, it is in front of it. In this diagram, you may have noticed that if the angle difference between the vectors is less than 90 degrees, the point is in front of the plane. If the in count was never incremented when we tested the plane against every corner, it means every corner of the box was outside of that plane, and thus the box is completely outside the frustum. We can return early. If both the in count and the out count have been incremented, then we set the result to intersecting preemptively. The box's plane could be intersecting the frustum, but might not be. The planes are infinite, so intersection does not necessarily imply collision with the bounded frustum volume. If we never encounter a situation where all the box's corners are outside a plane, hence the in-vertex count equals 0, and the result has been set to intersection in a prior iteration, then the box must be intersecting the actual volume, and this result will return at the end of the function. We reset the in and out counters after testing a plane on the frustum, so each plane's test is independent of the others. If none of the corners are outside any of the frustum's planes, and the result has not been set to intersecting, then the box must be fully enclosed in the frustum, and it will return the inside enumeration as it was initially set to at the start of the function. The test against an oriented bounding box works in the exact same way. The frustum sphere function first determines if the distance between the center of the sphere to one of the planes is longer than the radius. If so, we can exit early. There is no collision. If not, we test if any of the infinite planes are intersecting the sphere. If we find one that is, we find the closest point on the sphere to that plane, then see if that point is enclosed within the frustum. The sphere plane static function calculates the dot product between the sphere's position and the plane's normal to get the distance of the sphere along the normal. This value could be positive or negative. It then subtracts the plane shift constant from this value to get the distance from the plane's surface to the center of the sphere. We convert this potentially negative value to positive using the Fab's f function, then check if it is less than or equal to the sphere's radius. If so, there is collision. Refer to my previous video for a more in-depth explanation on plane mathematics. In the closest point on or within sphere to plane function, we find the closest point by calculating the distance between the plane and the sphere's center along the normal of the plane. Recall that this is the dot product of the plane's normal and a vector between the point on the plane and the center of the sphere. We clamp the distance by the radius so that the point will be on the surface of the sphere if the sphere is not intersecting with the plane, but within the sphere if it is intersecting. In our scenario, intersection has already been confirmed, but this lets you understand the function as a standalone unit. We then create a vector with a magnitude of the distance that is pointing towards the plane, which is why we negate the normal vector. Once we add this to the sphere's center, we have the point closest to the plane. Back in the frustum sphere function, we use the frustum point function to see whether the point is on the surface of the frustum volume rather than just on the surface of one of the infinite planes. Similarly to the axis-aligned bounding test, we test if the closest point on the sphere is in the positive half space of any of the frustum's planes by using the distance function. If it is, then it is not intersecting with the surface of the frustum. It was just intersecting with one of the infinite planes. Otherwise, the function returns inside, and we return intersecting in the calling function. If neither the outside nor the intersecting scenarios are identified, then the sphere must be enclosed within the frustum, so we return inside. Thanks for watching.